Start?
No, let me
Okay.
give an introduction. So yeah, hello everyone. Welcome to the theory seminar. Thanks for joining us. So today we have Mitali Bafna to talk about her latest research. Mitali is a graduate student at Harvard, advised by Professor Madhusudan. Before this, she was an undergrad at IIT Madras. She's currently supported by the Siebel Scholar Award for 2021. Her research is broadly in theoretical computer science with a focus on complexity theory and algorithms for fundamental optimization problems. She has published papers in top theory conferences such as STOCK, SODA, CCC, COLT, and so on. Mitali, thanks for joining us today. Over to you.
Thanks. Uh, so I'll just share my screen. Okay, so you can see my screen, right?
Yes, yeah.
Okay, so hi everyone. Today I'll be talking about this paper, Playing Unique Games on Certifiable Small Set Expanders. This is joint work with Boaz, Pravesh, Sleel, and David. And feel free to stop me with questions. I have not created like a very long talk, so there's a lot of room for questions. So let me start with defining the unique games problem. An instance of an affine unique games problem is a CSP, so a constraint satisfaction problem on n variables and m equations, where each equation is of the form xi minus xj equal to some constant s modulo k. So the important thing is that each equation has only two variables. And sorry, can you see my cursor?
Yes, you can.
Okay. So each equation has two variables, and the right hand side is some constant integer between 0 to k minus 1. And we want to solve these equations modulo k. So the value of an instance is the number of equations that can be satisfied by by the best assignment to x. So since each equation is on two variables, this instance can be viewed as a labeled graph instance, where we map the variables of the equations to the vertices of the graph, and we map the constraints in the equation in the instance to the edges, and finally the shifts or like the right hand side of the constraints are put as labels on the edges. And what we need to do is find an assignment to the instance. And this corresponds to labeling the vertices of the graph with something in 0 to k. And just to avoid confusion, we can just think of every constraint as in every edge in the graph as xi minus xj equal to some shift s with I less than equal to j. So there will be a direct one-to-one correspondence between the instance, like the equation view of the instance and the graph view of the instance. Okay, so now let me define the C, S unique games problem. This problem asks us the following, that if there is an instance of unique games such that there is an assignment that satisfies some C fraction of the equations, we are asked to find an assignment that satisfies at least S fraction of the equations. So we are thinking of C as larger than S, and both are some constants in 0 to 1. Now the Unique Games Conjecture, proposed by Cote in 2002, says the following. So for all constants epsilon, there exists a large enough constant alphabet k such that the C, S unique games problem, where C is equal to 1 minus epsilon and S is equal to epsilon, this is NP hard. So what this says is that even if we are given the promise that there is an assignment that satisfies, let's say, 99% of the equations, it is hard to find an assignment that satisfies even 1% of the equations. And like if you want to increase it to 99.9, etc., you can take a large enough alphabet K such that this problem is still hard. So this conjecture might look a bit weird, but it turned out to have a lot of implications in hardness of approximations. So in fact, it implies optimal hardness of approximation results for many problems in combinatorial optimization, such as finding a vertex cover in the graph or finding a maximum cut in the graph, and in fact, all constraint satisfaction problems. So any questions up till here? Okay, so if there are no questions, let me go into what is known about this conjecture. So it's turned out to be really like it's turned out to be hard to even know whether this conjecture is true or false. Up until 2018, it was believed that it could be false also. But in 2018, the breakthrough of these authors, Khote, Minzer, Safra, Dinur, and Kindler, these authors proved that the unique games problem with completeness half, C equals half and S equals epsilon is NP hard. So what we wanted to prove, the unique games conjecture says that C equals 1 minus epsilon, so something like 99% versus 1% is NP hard. But what they were able to prove is unique games with 50% of the equations being satisfied and distinguishing it from, let's say, just 1% of the equations being satisfied, that is NP hard. And why has it been so hard to prove this conjecture? So it turns out that there are very non-trivial algorithms for the unique games problem. So firstly, in contrast to, let's say, the canonical NP-hard CSPs that we know, such as 3-SAT and whatever you can think of, like 3-coloring, etc., there are very non-trivial algorithms. So firstly, there are sub-exponential time algorithms for all unique games instances. So just recalling that for 3-SAT, it's a conjecture that it does not have any algorithms that beat brute force. So you cannot solve it in 2 to the little o of n time. Whereas here we have sub-exponential time algorithms. And then we also know that unique games is easy on many restricted families of instances, including expander graphs, perturbed random graphs, and graphs with small threshold rank. So again, one interesting fact here is that expander graphs are actually random instances of unique games, because suppose if you sample random graphs, they will be expanders. So what this result AKKSTV and MM10, these results basically say that random instances of unique games are easy. And again, contrasting with 3-SAT, there is a conjecture that random instances are also hard. So that's why it's very interesting. And up till 2018, there was no consensus on whether this conjecture is true or false. Now, let me give a little bit background about Sum-of-Squares algorithms, which and basically all the algorithms I just told you about turn out to be Sum-of-Squares algorithms. So the Sum-of-Squares hierarchy, or the Lasserre-Perillo hierarchy, is a hierarchy of increasingly powerful semi-definite programming relaxations for polynomial optimization. The degree of Sum-of-Squares basically measures the level in the hierarchy. So how good of a relaxation it is. So I will not go into too much detail, but you can just think of it as the degree ranging from 2 to n, and degree 2 will be the lowest level of the hierarchy, so the weakest algorithm, and then degree 4 will be stronger, and so on, and up till degree n. Um, and solving the degree D sum of squares program for an optimization problem. This corresponds to, oh yeah, so let me also mention that basically for unique games or any constraint satisfaction problem, there is a canonical relaxation, convex relaxation using sum of squares. And we can make it more and more powerful by increasing the so-called degree of this relaxation. So these are all canonical programs for the problem. And solving the degree D sum of squares program gives us this object called the degree D pseudo distribution. And basically this is like just like a solution to the problem, but it's like a convex relaxation, and using that we need to find a solution to the unique games problem. So any questions about this? I'm just being very vague about this because I will not be going into too many details, so it's not required to know these things for the talk. Okay, and then one more very related concept here is sum of squares proofs. So the sum of squares proof system is a restricted proof system for proving polynomial inequalities. And again, the degree of the proof measures the complexity of the proof. So how hard of a proof it is. And this ranges again from degree 2 to degree n. And these two concepts of sum of squares proofs and sum of squares algorithms are very intimately connected. And this connection has been exploited to obtain efficient algorithms for a variety of problems. So if you did not understand these two slides, it's okay, you can understand the rest of the talk. So now let me define expansion in graphs. Given a d-regular graph, expansion of a set in the graph is defined as the fraction of edges that leave the set, where we are normalizing by the total number of edges incident on the set. So the fraction of edges that leave the set are so this notation just means the edges that go between S and the complement of S, and divided by the degree times the number of vertices in the graph. So for example, if we take an independent set in a graph, all the edges would leave the set. So the expansion would be 1. And similarly, if you take, if you take a isolated component, the expansion would be 0. So we will be considering, since we are giving unique game algorithms on graphs which expand in certain ways, let me define these expander graphs and small set expander graphs. So a graph is an epsilon expander if all sets in it, so we consider only at most half-sized sets, have expansion at least epsilon. And a graph is a small set expander, so epsilon comma delta small set expander, if all sets of size at most delta n have expansion at least epsilon. So this is a more relaxed notion because here we want all sets up till half size to have large expansion, whereas here we want all sets of size at most delta. So delta can be thought of as some small constant like 1/1000. We only want all sets up to this size to have large expansion. So as you can see, small set expanders are a larger class of graphs than expander graphs. So now let me define certifiable small set expanders. These are the class of graphs that we give algorithms for. So a graph G is a epsilon delta comma D certifiable small set expander. If firstly that it is a small set expander, so it is an epsilon comma delta small set expander. But furthermore, this fact that it is an expander has a low degree sum of squares proof. So if you don't know what a sum of squares proof is, this just means that it is easy to certify that it's a small set expander. So it's easy to basically check that it's a small set expander. So in general, it could be hard to check this because we have to go over all sets and check if they expand. But because there is this sum of squares proof that it's an expander, this fact becomes easy to check. Now I will state our results. We firstly show polynomial time sum of squares algorithms for approximating unique games instances over certifiable small set expanders. And in fact, our algorithm is pretty versatile because it also generalizes to Johnson graphs. And these are graphs that are not small set expanders. But I will discuss why we can generalize this algorithm on small set expanders to Johnson graphs. And in fact, I will mention that in recent work, we have even generalized it to high dimensional expanders. Again, these are classes of graphs which are not small set expanders, but they have nice properties. And they are actually a generalization of Johnson graphs. Today, I will discuss the first result in more detail. So firstly, what is the motivation to study unique games on restricted classes of graphs? Firstly, we don't know any hard instances of unique games. So we don't even know conjectured hard instances because whatever instances we come up with, there are sum-of-squares algorithms or some easy algorithms for it. So it is known to be easy, as I said before, on random instances, which are expander graphs, and on perturbed random instances. So our algorithms on certifiable small set expanders imply a new connection between the unique games conjecture and the small set expansion hypothesis. So this small set expansion hypothesis says that the problem of distinguishing whether a graph is a small set expander or it is not a small set expander is also NP-hard. And basically this, we do not know whether the small set expansion is as hard as the unique games problem. So it is known that the small set expansion problem is reduces to the unique games problem. So that is that it is easier than the unique games problem. But we do not know whether the unique games problem reduces to the small set expansion problem. So it could be that the unique games problem is much harder than the small set expansion problem. But our result shows that in certain regimes, when, for example, the small set expansion problem has a sum of squares algorithm, then also the unique games problem has a sum of squares algorithm. So at least in the sum of squares world, it's not much harder than the small set expansion problem. And one interesting thing is that this Johnson graph, which I just mentioned, the Johnson and related Grassmann graphs were used in the construction of these NP hard instances. So they were used in the resolution of the 2-to-2 game conjecture, which I mentioned some time back. And in fact, the main proof ingredient there was characterizing the non-expanding sets in these graphs. And they use this characterization to get hard. So to prove this unique games is hard with half comma epsilon. And we use the same kind of characterization to give algorithms. And that therefore this highlights a fascinating interplay between algorithms and hardness. So any questions up till here? Okay, so now I'll mention some connections between Sum-of-Squares algorithms and unique games. So firstly, Raghavendra showed in a very exciting result that the unique games conjecture implies that the lowest level of the Sum-of-Squares algorithms, so just the degree 2 level of the hierarchy, is the optimal algorithm for all constraint satisfaction problems. So whenever you're given a constraint satisfaction problem and you want to approximate it, you can just write the canonical convex relaxation for the problem. And in fact, just the lowest level of the relaxation, and that would be the optimal answer. So that would be like the optimal algorithm. And this is a very surprising fact, at least for me. And therefore, as the history goes, this theorem was very surprising, and therefore many people tried to refute the unique games conjecture by studying higher levels of the Sum-of-Squares relaxation. And this led to some techniques such as global correlation rounding of Barak, Raghavendra, Steurer, and this proofs to algorithms perspective of these authors. These techniques were developed to analyze these Sum-of-Squares relaxations. And these were, although they were developed for unique games, they have led to a lot of breakthroughs in high-dimensional statistics, quantum computation, statistical physics, and other problems like that considered in Raghavendra Tan. So let me highlight here that it is always easy to write a convex relaxation, but it's not easy to see whether, so the non-trivial part comes in analyzing the algorithm. So there is a very canonical algorithm, but we do not know whether that algorithm is good or bad. So the analysis of the algorithm is the hard part. And therefore, these techniques were developed to analyze these Sum-of-Squares algorithms. Now I'll discuss our results. Firstly, we give a new technique for rounding higher degree Sum-of-Squares relaxations. We show that polynomial sized Sum-of-Squares relaxations solve unique games on graphs that were out of reach of previous techniques. So these graphs are short code graphs, the noisy hypercube, and Johnson graphs. And previous algorithms, for example, that of Barak, Raghavendra, Steurer, and Aurora, Barak, Steurer, these required quasi-polynomial time for the noisy hypercube and sub-exponential time for the short code and Johnson graphs. And our algorithms require polynomial time for all of these graphs. And to illustrate, firstly, the noisy hypercube and the short code graph, these are small set expander graphs. And furthermore, they have low degree sum of squares proof. So that is the fact that we use, that they have a they are not only small set expanders, but they are easily certifiable with degree 4 sum of squares. And the interesting thing is that we know that it requires degree 4 to solve these graphs, because if you know what is an integrality gap, the noisy hypercube and shortcode graphs were integrality gaps for degree 2 sum of squares. So we know that degree 2, so the lowest level cannot solve these graphs, but higher levels can. So now I'll go into some details of the theorem, and if there is time, I will describe a small part of the proof. Before that, are there any questions? Okay, so so let me describe our first theorem on certifiable small set expanders. We prove that for all epsilon and delta in 0, 1, and degree D, so this is the degree of the certificate. And suppose a graph is a epsilon delta D certifiable small set expander. So to recall, the graph is such that all sets of size delta, at most delta, have expansion at least to epsilon. And there is a certificate. So think of this as some easy proof that this fact is true. And now consider a unique games instance on this graph that is at least 1 minus epsilon satisfiable. So we can so there is an assignment that satisfies 1 minus epsilon fraction of the equations. Then there is a polynomial time algorithm that finds omega 1 satisfying assignment in time which is polynomial in the vertices, and the polynomial constant depends on epsilon, delta, and D. So recall that to solve the unique games problem, we only, given a 1 minus epsilon instance, we only need to find an epsilon satisfying assignment, like some constant satisfying assignment. And that's what we do. And this constant would depend on the graph parameters, which are epsilon and delta. If you're familiar with the previous unique games literature, I would just like to mention that the new thing here is to get a is that basically this epsilon parameter can be whatever, like basically it doesn't have to be really small. Our algorithm works for all epsilon and delta. And previous algorithms would work only for epsilon, which is small enough as a function of delta.
So what is the fraction of constraints that are satisfied?
Yeah, that would be some, so it will be something like epsilon times delta squared.
Okay.
Yeah.
Because something like BRS would give you 1 minus order epsilon. Wondering how this.
Yeah, exactly. But BRS, yeah, but the issue is that BRS will take a lot of running time. Whereas to solve the unique games problem, it's enough to find like a small satisfying assignment. So
okay, you mean solving in the regime of the unique games conjecture?
Yeah, exactly. And okay. BRS would take so BRS would give actually a stronger guarantee on the approximation factor. It just always gives, yeah, as you said, 1 minus epsilon versus 1 minus epsilon minus some nu, which is an additive constant. But it requires sub-exponential time for shortcode, for example. and like quasi-polynomial time for noisy hypercube.
Okay.
And if you know about it, so the basically BRS depends on the threshold rank of the graph. So if the graph has a lot of eigenvalues near 1, then it will take exponential in that time. So if it has t eigenvalues near 1 minus epsilon, then it would take 2 to the t time. But we observe that the short code graphs and noisy hypercube, they have a lot of eigenvalues, but they are still small set expanders. So we don't need to pay 2 to the t in the running time. We only need to pay this d, like d factor, 2 to the d, n to the d. And for example, for noisy hypercube and short code, this d is just equal to 4. Okay, so if the theorem statement is clear, I will go to some ingredients of the proof. Firstly, let me describe what's the algorithm. So this is the algorithm for certifiable small set expanders. The Johnson algorithm is slightly more complicated. It's like a kind of recursion, and I can discuss it more in the end of the talk. So first, let's assume we are given an instance, which is a graph, and labels on the edges of the graph. And this instance is 1 minus epsilon satisfiable. And of course, we know that G is a 2 epsilon comma delta comma D certifiable small set expander. And our goal is to return an assignment to the vertices of the graph that satisfy a large, like a constant fraction of the constraints. And sorry, I forgot to mention that this constant has to be independent of K. K is our alphabet size. Basically because a random assignment satisfies 1 by K of the fraction of the edges always. So we do not want to pay in the alphabet size, but we are okay with paying something in epsilon and delta. Yeah, because in general, the alphabet could be really large, but that's why we don't want any dependence on alphabet size. Okay, so what is the algorithm? Firstly, we write a convex relaxation for the problem. So it's a degree D. If this is our graph is D certifiable, then we write a degree O of D Sum-of-Squares program for the instance. And this after this, we obtain a 1 minus epsilon value degree D O of D pseudo distribution for the instance. So for this talk, it's enough to think of this pseudo distribution as a distribution over the satisfying assignments of the instance. So given an instance I, which is 1 minus epsilon satisfiable, there will be many solutions for I, which are 1 minus epsilon satisfiable, right? And what we obtain after writing the relaxation is a distribution over these over the assignments. And we are given the guarantee that, let's say, each of these assignments has good value. So we have each assignment is 1 minus epsilon valued. So obviously, if we were given a distribution over the assignments, our algorithm could just be to sample an assignment from the distribution. But the hard part is that the access to the distribution is only using the low degree moments of the distribution. So for example, you're given information about the mean of the variables and the variance and the covariance and degree 3 moments, etc. So first, like if it's unclear, firstly, the variables in our distribution are just going to be y1 to yn, and each yi takes value in. So each assignment is assigning something in 0 to k minus 1 to each variable, and the distribution will be over these y's. So we will be given information about what is the marginal information for y1. So basically, what is, if you take marginal over the first variable, then uh, then like with what probability is it equal to 1, with what probability is 2 up to k minus 1, etc. And then the degree 2 moments will be the expectation of y1 and y2 over the distribution, and so on. So now it's not even clear that given this low degree information, why is it at all helpful to get a solution? So given this low degree information, we can actually perform a very simple algorithm, which we call condition and round. And this requires only degree 2 information for the algorithm requires only degree 2 information of the distribution. So the first step is to just sample a random vertex and a random label in 0 to k minus 1 and condition the distribution on the vertex u taking the value L. And this gives us a new distribution, conditioned distribution. So mu conditioned on the vertex u taking the value L. So is this step clear? Okay. And then the second step is we randomly choose the values of all the other labels independently according to the marginals. So we have conditioned the distribution, and for each variable we take its marginal. Its marginal will be a distribution on 0 to k minus 1, and we sample a label from the marginal. So for each vertex we just get a label and just output this as a solution. Now, as you can see, the algorithm is very simple, but basically all the work goes into analyzing the algorithm and proving that this is a good satisfying assignment. So actually I wanted to write something, or let me see if I can share screen. In the meanwhile, let me know if there are questions.
So this algorithm is very reminiscent of BRS, but here you're conditioning only on one variable instead of a large number of them.
Yeah, exactly. So in BRS, what they do is they keep conditioning on many variables, and then in the end, they perform this step.
So is the proof similar? Is going to show that the y's have small variance after conditioning?
Yeah, in some sense, yeah, because it is a small set expander, they will have small variance after conditioning. But the proof is pretty different because there they rely on different properties of the graph G. As I said earlier, they rely on this low threshold rank property, and their proof doesn't work on when G has large threshold rank. So we have to do a completely different proof, and plus like their algorithm is more general and works on all 2 CSPs, whereas our algorithm is very specific to unique games, and therefore this we can exploit the small set expansion property of the graph.
Okay, so I guess even here you'd probably be showing that the solution has a large global correlation or something.
Yeah, actually we won't be showing that. Like we exploit a totally different property.
Or at least implicitly something like that should be true, right? Because if after conditioning on one vertex, all the marginals have small variance, that seems to suggest that the variables are highly correlated, right?
Oh, sorry, one second. Why is there this? Like I joined from my iPad, but there is a.
So I think you should mute one of the two devices.
Yeah, I think you're on mute in both of them. Maybe you need to put the volume on 0 on your iPad.
Oh, okay. Now it's fine, right?
Yes.
Okay, thanks. Okay, yeah, I think, okay, I'll just write something at the end of the talk. Sorry, there was a question earlier, right, about the global correlation.
No, so I was saying that since the algorithm you're saying you condition on one vertex and then sample from the marginals of the other variables.
Yeah.
Doesn't that seem to imply that there is some large global correlation?
Yeah, there is large global correlation, but so in the BRS algorithm, what happens is there is large global correlation, but it implies there is low global correlation and it implies low local correlation, and that's why this step 2 works. But we cannot show that it implies this local correlation. But we can still show that the algorithm works. So local correlation is the correlation on the edges of the graph, and global correlation is just the correlation when you sample two random vertices. And we always need local correlation to be small for this, like for at least for the BRS analysis. Okay, so to illustrate why this algorithm could be useful, I will just give an example that let's say you have a very simple distribution where you just take one assignment and take all its shifts. So let's say the first assignment was, let's say just for simplicity, all zeros. Then, and this is 1 minus epsilon satisfying. Then you can take a uniform distribution over all zeros, all ones up till all k minus ones. And this would be a valid distribution. Now, what would the first step do? The first step will condition the value for the first variable, or let's say like u equals 1, and we condition it to let's say a random label which is equal to 2. So now once we condition it, our distribution gets fixed to this assignment. And now if we just sample a solution to each of the variables randomly, all of them will get sampled to 2. And therefore we will recover the solution all 2s. And that's why we recover 1 minus epsilon satisfying solution in this case. Now, obviously, we are not guaranteed that our solution is going to be supported only on one assignment and all its shifts. But basically, when it's a small set expander, we can get that it's supported on solutions of low variance. Okay, so first let's do a thought experiment to analyze this algorithm. Consider two assignments, x and x prime, and consider the following partition of the vertices of the graph. So we have the first partition C0 of x comma x prime, where we put in all vertices u, where xu minus xu prime is equal to 0 modulo k. So just recall that each variable xu takes some value between 0 to k minus 1. And we just put in all the vertices in the 0th component, where xu minus xu prime, the difference between the two assignments, is 0. And then similarly, we do it for C1 and up to ck minus 1. And now the interesting thing we exploit is that any edge that goes between two different components, so Ci and Cj, where I is not equal to j, is violated by either the assignment x or the assignment x prime. So consider the edge uv, and let's say u is in component Ci and v is in component Cj. So by just the properties of Ci and Cj, we have that xu minus xu prime is equal to I, and xv minus xv prime is equal to j. And now let's subtract these two equations, and we just get that xu minus xv minus xu prime minus xv prime. This is equal to I minus j, and since I is not equal to j, this is non-zero. So what does this mean? That suppose the edge was satisfied by both the assignments, we would have that this edge xu minus xv is also equal to the label on the edge, and so is xu prime minus xv prime. And therefore, if we subtracted these two quantities, they would have been 0. So that's why it cannot be satisfied by both the assignments. And this means that when we create this shift partition, there can be at most 2 epsilon fraction of edges that are violated by x or x prime, and that's why the fraction of edges that go between the components is at most 2 epsilon. This is just because of a union bound, and because we know that x is a 1 minus epsilon satisfying assignment, and so is x prime. And now we are able to use that G is a small set expander, and that's why one of the components must be of size at least delta. So this is just a very simple like averaging argument. We know that if a set has expansion at most epsilon 2 epsilon, then it has size at least delta. And now we can also do the same argument where you have a partition of the graph and the fraction of edges crossing are at most 2 epsilon. Any questions about this? Okay, so so just to formalize this, we define a potential function called the shift partition potential of the so that depends on the graph and on the distribution we are given. And this looks complicated, but it's basically the same idea which I just said. We take an expectation over all possible assignments, x drawn from mu, and another random x prime drawn from the same distribution mu. So these are drawn independently. And we take the sum of squares of the sizes of these components. So x and x prime lead to a shift partition of the graph. And each part in the partition has size, like fractional size in the graph, which is this size of the component divided by the total number of vertices. And we take the sum of squares of these sizes. So this quantity is, for example, at most 1. If we didn't have the square, then it would be exactly 1. And this quantity can also be just written as this this thing, and that's why it's like a polynomial quantity in these variables xu and xu prime. So firstly, the argument I just said about that the fraction of edges crossing in the shift partition is at most epsilon, and that's why there has to be a large part. This can be formalized, and we can show that if the shift partition potential, so if this quantity is at least delta, sorry, if this if mu is a satisfying over a satisfying assignments, distribution over satisfying assignments, then the shift partition potential is large, is at least delta. So this and this happens only when we have this like sum of squares proof of small set expansion. So this is like a formalization of the argument I just said. And then the interesting thing is that so this is one part of the argument, that if mu is over satisfying assignments, then the shift partition potential is large. And the other part of the argument is that when it is large, then the condition and round algorithm outputs a good solution. So I was going to show the proof that it outputs a solution which is delta minus epsilon. I can show it in the end of the talk if people are interested. And the interesting thing is that this is independent of the graph or what kind of properties it has. So whenever this shift partition potential is large, we can get this assignment of value delta minus epsilon. But as I said earlier, what happens when delta is smaller than epsilon? Then this solution is useless because we want to handle all delta and all epsilon. So we actually, in our paper, define a complicated potential function. And we need to do a slightly more complicated analysis to handle this case. And now I'll just say a few things about Johnson graphs. So firstly, Johnson graphs are not small set expanders. I had showed that basically if you have two epsilon fraction edges crossing, then there has to be a large component. That's the place where we used that the graph is a small set expander. But what happens if you're not a small set expander? Some recent work shows that the structure of non-expanding sets in the Johnson graphs has a nice characterization. So there exists a family of subgraphs of the Johnson graphs, such that if you are a non-expanding small set, then you have to be correlated with a subgraph in the family. So so basically, where we use the small set expansion property of the graph, we use this property of the Johnson graph and show that this potential function is large on some subgraph of the Johnson graph. But then this subgraph might be really small. So we solve the Unique Games instance on the subgraph, but this might be only a little of one fraction of the whole graph. So then we again write a new Unique Games program and solve it on another small part of the Johnson graph, etc. And we keep like solving on small parts, and then finally we patch it together to a solution that is omega of one fraction of the graph. Thanks. And if there is time, I could show the proof.
Yeah, so there's one question from Ramesh.
Okay.
Who's asking, what is the motivation or justification for the particular form of potential function?
Yeah, so that justification, sorry, let me just leave from there. Yeah, so the justification comes, so the motivation comes from this, like the part which I didn't show. So analyze. So when the potential function is large, then proving that the condition and round algorithm works. So that proof is some is just something based on collision probability. Like that proof is not so hard. Actually, let me show what I was saying. So what I mean is this proof. This is not so hard. So in fact, when the potential is large, we can rearrange the form of the potential. Like we can rearrange these terms and show that the collision probability of some variables are high, and therefore the variance of the variables are low. So each variable is essentially like once you condition the distribution, each variable is essentially just supported on one point. So between 0 to k minus 1, each variable will be just one label, and therefore when we round independently, it works out. So yeah, that is the motivation to define this potential function. But then there are issues, like the issues come up when we try to get delta smaller than epsilon. So we modify the potential function a bit, and then still like we try to make part 1 go through and part 2 go through, but with a better value, something like delta times epsilon. And I would say the main motivation was basically just this thought experiment that I showed, that when that basically any edge that is violated, any edge that goes between components has to be violated. So the fraction of edges is small. So that is kind of just put into the potential. Are there other questions?
Okay, so if there are no other questions, Mitali, thanks again for this talk. Everyone, thank the speaker again. Let me stop the recording.